Alright everybody, welcome back to another in-class video. This video is for section 4.4, which is the net change formula and total area. So if we take a look at the first example here, example 4.4.7, it's saying if h prime of t is the growth of a tree in inches per year, what does the integral from 5 to 8 of h prime of t dt represent? Well, we can turn to our units for this. The units of h of t are in inches per year, and the units of dt are in years. So when we multiply those two things together, we should get inches for the units on our answer. What this integral tells us is that we're adding up all of the change from year 5 to year 8. So using the fundamental theorem of calculus, we see that this integral is equal to h of 8 minus h of 5. All h of 8 minus h of 5 is the change in the height from year 5 to year 8. And we're going to see that happen over and over in this section, that our integral of a rate of change is just the total change over the range of the integral. So let's go ahead and carry that theme to the second example here, example 4.4.8. Water flows from the bottom of a storage tank at a rate of 10 minus 2t liters per minute, where t is in between 0 and 5. It makes sense that t is in between 0 and 5 because we're starting at time 0. And then we have to stop at time 5 because that's when our rate hits 0. Alright, so after a minute, a 10-liter bucket is placed under the storage tank to catch the water. How much water accumulates in the buckets during minutes 1 and 2? So to calculate this, what we're trying to do here is on our timeline, we're starting at time 0. After 1 minute, that's when we put our bucket underneath the leak, and then through minutes 1 and minutes 2, so all the way up right until when minute 3 starts, that's when we're collecting the water. And we can represent this collection by doing the integral from 1 to 3 of 10 minus 2t dt. And now we can use a fundamental theorem of calculus to find the number of that integral. So when we find this integral, we're going to take the antiderivative of the 10, which is 10t. The antiderivative of 2t is t squared. We're going to evaluate this from 1 to 3, which means that we're going to plug in the 3 for every place that we see the t, and then we're going to plug in the 1 for every place that we see the t, and we're going to go ahead and subtract those two calculations to find our total volume accumulation from minute 1 to minute 3, which is the first minute and the second minute. So you see here that we have 30 minus 9 minus 10 minus 1, or 21 minus 9, which is equal to 12, and our units here are liters. So 12 liters of liquid. But wait a minute, this doesn't make any sense because the bucket only had a capacity of 10 liters. So the bucket must have been overflowing at some point. And we can actually use calculus to figure out when did the bucket start to overflow. So let's go and take a look at that for our next example. So we can do this with a little bit of a creative integral. So what we want to figure out basically is how long does it take for the volume to get to 10? Well, we can do this by setting up our integral. We know that we're going to start at minute 1, but we don't know when we're going to finish. What we're trying to figure out is at what time x does the bucket start to overflow. And our rate at which the bucket is filling is the same as in the first example. So what we can do here is we can take the antiderivative again, 10t minus t squared, and now we're going to integrate from 1 to x. And when we do that, we're going to get 10x minus x squared, all subtracted 10 times 1 minus 1 squared. And so we have 10x minus x squared minus 10 plus 1, or negative x squared plus 10x minus 9. And this is all equal to 10 because we're trying to find the x value when the volume is equal to 10. Now, remember, to solve a quadratic equation, we need the equation to be equal to 0. So we have negative x squared plus 10x minus 19 is equal to 0. And this, unfortunately, is not factorable. So the quadratic formula states that x is equal to negative b, which is 10, plus or minus the square root of b squared, which is 100, minus 4 times a, which is negative 1, times b, which is negative 19, all divided by 2 times a, which is negative 1. Now let's do some simplification. And when we do that simplification, we get negative 10 plus or minus the square root of 24 over negative 2. Simplify that one. And if we want to get a little bit better simplification here, we get 5 plus or minus the square root of 24 over 2. Now 24, the square root of 24 is about 5. So this is about 5 plus or minus 2.5, which is about 2.5 or 7.5. And 7.5 doesn't make any sense, but 2.5, that makes a lot of sense because we found out that if we went from 1 to 3, it overflowed. So somewhere in between 1 and 3 is where it must have hit exactly 10 liters. So in this case, our t value that we're looking for, or our x value, is that this happens at the time 5 minus the square root of 24 over 2. That's the exact time when the bucket starts to overflow with 10 liters of liquid in it. All right, well, that's a little bit crazy. Let's see what the next example has in store for us. So now it says at time 4, a new bucket is placed underneath the storage tank to catch the water. How much water does this bucket have in it at the end? Well, here we're just going to be doing the integral from 4 to 5 because we knew that our rate is going to stop at 5, given up here in our original domain that the flow stops at time 5. So we're going to do the exact same integral, the integral from 4 to 5 of 10 minus 2t dt, which is again going to be 10t minus t squared, but now our bounds have changed to be from 4 to 5, and now we're just going to go ahead and substitute those in. So we get 10 times 5 minus 5 squared, all subtracted from 10 times 4 minus 4 squared. And if we go ahead and simplify that, we get 50 minus 25 minus 40 minus 16. So we have 25 minus 24. And that just gives us that 1 liter of water is all that we had in that last minute of flow. So looking back through these problems, what we have is first we're doing the integral from 1 to 3 because we want to figure out how much water accumulated in minutes 1 and minutes 2, which is the integral from 1 to 3. That would have been 12 liters. That would have overflowed our bucket. So then we wanted to figure out, well, when did the bucket start to overflow? So we chose our integral. The upper bound of our integral was x, and then we solved for x. And we found that that happened at about 2.5, which makes sense because when we integrated from 1 to 3, we had our overflow. So it should have been right before 3. And now, for the last problem, we integrated from 4 to 5 to figure out how much water accumulated in the second bucket that we put underneath our leak. And we figured out that 1 liter accumulated in the last minute. Alrighty, so let's take a second here. I'll give you 5 seconds to pause that if you want to take a look at some of that work, and then we're going to move on to our next example. All right, let's take a look at the next example here. So on the next page of the notes, we are going to figure out how to calculate the total distance traveled by an object moving in a straight line between time A and time B. And this is a little bit different than the total displacement, which we would have found out by just finding the position at time A and the position at time B. To find the total distance, we want to be adding the positive and the negative distance traveled, all as positive numbers. So we want to be adding up all the area that's traveled in between time A and time B, and we want to take the absolute value of the velocity function because that is going to give us a positive distance regardless of what direction we're traveling in. And notice that's a little bit different than just finding the integral from b to a of the velocity, because then when we have positive velocity, we're adding to the distance, and when we have negative velocity, we're subtracting from the distance. But when we're integrating the absolute value, we're always adding to the distance, and that's how we're going to get the total distance traveled. In general, we can find the total area under a curve by doing the integral from a to b of the absolute value of the function. What this is going to do, just like in distance, is this is going to add all of the areas together rather than having the area underneath the graph acting as negative area that's being subtracted. So let's put this to use. So let's try to, first we're going to do a regular integral here. We're going to integrate x minus 1 from 0 to 2. In order to make sense of this, let's sketch a graph really quickly. Alright, so here's a sketch of our graph. And now what we can expect is we can expect the area that we're finding when we're doing this integral from 0 to 2 to be 0. And that is because we have this area from 0 to 1, which is negative, and this area from 1 to 2, which is positive. They counteract each other exactly. We can use the area of triangles to actually see. This first area right here, from 0 to 1, is 1/2, and the area from 1 to 2 is also 1/2. But when we do the integral, we're going to get 0 because the area underneath the graph is a signed area of negative 1/2. We can see that when we do the antiderivative. We get x squared over 2 minus x, and we're going to evaluate that from 0 to 2. Now when we plug in a 2, we get 4 over 2 minus 2, and when we plug in a 0, we get 0 minus 0. And so total, we have 2 minus 2 minus 0 minus 0, and if we do that subtraction, we just get a 0 there. But there's another calculation that we might want to do. We might want to see that the actual area enclosed here is 1 if we did the 1/2 plus 1/2. That's the kind of thing that we would want to do if we were trying to find the total distance traveled. Example 412 is doing that calculation. We're going to find the integral from 0 to 2 of the absolute value of x minus 1. Now I can draw that in here on the graph. That absolute value is going to flip this part of the function from 0 to 1 over the x-axis, so we have a positive area of 1/2 here. And then 1/2 plus 1/2 is 1. But to calculate that using the integral, we have to think about something a little bit different. What we need to do is we need to recall that the absolute value of x minus 1 is equal to a piecewise function, x minus 1, where x is greater than or equal to 1, and negative x minus 1, where x is less than 1. Another way to think about this is that we took this function right here, negative x minus 1, and we glued it to positive x minus 1 right at that x equals 1 value. And what that means is that in order to calculate this using integrals, we're going to need to do the integral from 0 to 1 of x minus 1 and the integral from 1 to 2 of x minus 1, and we're going to need to add the absolute value of those integrals together. Now, that's because the integral from 0 to 1 of x minus 1 is actually this red triangle, so we're going to get a negative number for this integral from 0 to 1. But we're going to take that negative 1/2, find the absolute value of it, which is the positive 1/2 that we see here in the blue triangle, and then we're going to have positive 1/2 plus positive 1/2 to get our area of 1 that we expect. Let's go and see how that works out with the calculus. So we're going to do x squared over 2 minus x evaluated from 0 to 1. And when we do that, we get 1/2 minus 1 subtracted 0 minus 0, and that gives us, like we expected, our negative 1/2. But we are taking the absolute value of this negative 1/2. And what we're going to do is we're going to add that to our antiderivative, which is x squared over 2 minus x evaluated from 0 to 1. And again, we're going to take the absolute value of that part of the function. We don't really need to worry about taking the absolute value of the second part because it's already going to be a positive number. When we calculate this, we get, the bounds here need to be 1 to 2. When we calculate this, we're going to get 4 over 2 minus 2 minus 1 over 2 minus 1, which gives us a 0 minus a negative 1/2, which ends up being a positive 1/2. So then when we take the absolute value of negative 1/2 plus 1/2, we end up with 1 as the integral of the absolute value, And this is our total area from x equals 0 to x equals 2. All right, well, that wasn't too bad when we were doing this linear function because we were able to verify it using our geometry areas of triangles. But now let's do this with a little bit more complicated function. Let's take a look at the integral from -2 to 2 of x squared minus 1. Let's go and get a graph of this. All right, so there's a graph of our function, and let's go ahead and draw our areas on here. So we're going to have this area from -2 to -1, and this area from 1 to 2, which are just going to be the regular integrals of x squared minus 1. Now you can see here that we have this flipped area, which is coming from the original function, which would have been the parabola underneath the graph. And this is actually negative x squared minus 1 if we're taking a look at the piecewise function. In other words, what we're going to have here is that the absolute value of x squared minus 1 is equal to the piecewise function x squared minus 1 when x is less than 2 or negative 2, or when x is greater than 2. And it's the absolute value of x minus 1 is equal to negative x squared minus 1, where x is in between our negative 2 and our positive 2 values. So what we're going to need to do here is we're going to need to calculate the integral from -2 to -1 of x squared minus 1 dx, and then we're going to need to calculate the integral from -1 to +1 of x squared minus 1 dx, and then we're going to need to calculate the integral from +1 to +2 of x squared minus 1 dx. And we're going to need to take the absolute value of this middle part, because that part will be negative if we had it flipped around to use the negative x squared minus 1, because that would originally be finding the area here underneath the graph. So we take the absolute value after we do that calculation. We're going to get the positive area that we're going to want to add in to get our integral of our absolute value of our integrand. So let's go and do this antiderivative work. So the antiderivative of x squared is x cubed over 3, and the antiderivative of -1 is negative x, and we're going to evaluate that from -2 to -1. And we're going to take that and we're going to add this to the absolute value of x cubed over 3 minus x evaluated from -1 to +1. And then we're going to add to that x cubed minus 3 over 3 minus x evaluated from 1 to 2. So now this is going to be kind of messy to write out. So let's go ahead and take our time doing that. All right, so there's all of our antiderivatives with all of our endpoints plugged in. And remember, we're going to be taking the absolute value of this middle difference. So now let's do one more step of simplification. Woo, that's a lot of simplification. And we do have one more step of simplification. This problem is never going to end. Oh my goodness, there's the next step of simplification. We're almost done. Let's do a little bit more. So we get 4/3 plus the absolute value of -4/3 plus 4/3. That gives us 12/3. And oh my goodness, our area, our total area here is just 4. All of that work, and we get the answer 4. Okay, so take a second there. Copy down those notes if you need. And now let's try to write in words a general solution method for what we just did. So what we're doing here is we need to figure out where f of x is equal to 0. And we use that to break up the interval into pieces. So in the last example, we took our interval, which was from -2 to +2, and we broke it up at each one of the zeros at -1 and +1, so we had 3 different integrals. Then we need to calculate the integral on each piece and make it positive by taking the absolute value. And then we add together all of those chunks. All right, you should get some practice on that on web work, but the general idea here is that we're just splitting up the integral wherever we have our zeros, and then we're doing the integral on each chunk. We take the absolute value of every chunk, but it's only going to matter for the chunks that are negative, and we're just going to make those negative chunks positive, add them all together, and we get our total area. Alrighty, let's take a look at our next problem here. So our next problem here, this is WebWork 4.4, number 5. What we're given here is that the area of the black vertical lines is 24. Let's write that outside of that so it's a little bit easier for everybody to see. So the area inside there is 24, and the area inside this gray part is 8. So what is the integral from a to c then? Well, the integral from a to c would be 24 minus 8, because this area of 8 is underneath the x-axis. So we're taking the regular integral, the area is a negative area, and thus our total area is 16. Or not the total area, the integral area. When we're taking the integral of the absolute value, this is like finding the total area. So we're going to do 24 plus 8 because we found the absolute value, which is going to be a positive 8 area up there. And so when we do 24 plus 8, the area that we get is 32. Notice that we're going to do 24 minus 8 when we do the regular integral, and 24 plus 8 when we do the absolute value integral. So let's go ahead and take a look at one more example of this, and then we have one more applied example, and then we'll be done with the 4.4 video. So example 16 here is number 6 in your web work. We want to find the total area between this curve and the x-axis, between x equals -4 and x equals +4. So what we're going to need to do here is we're going to need to do the integral from -4 to +4 of the absolute value of x squared minus x minus 6 dx. And remember, what we're going to do is we're going to set our integrand equal to 0 to find the zeros of the integrand. We're going to solve this one by factoring. We can factor this into x minus 3, x plus 2, which tells us that there's zeros at x equals 3 and x equals -2. Then we're going to split up our integral using those new zeros. So we're going to go from -4 to -2 of x squared minus x minus 6 dx, and then we're going to find the integral from -2 to 3 of x squared minus x minus 6 dx, and then we're going to find the integral from 3 to 4 of x squared minus x minus 6 dx, and we're going to do the absolute value on each one of these chunks, but only the middle chunk is going to be the chunk that's going to be negative and have to be absolute valued. Now, let's go ahead and find our antiderivatives. So in each case, the antiderivative is going to be x cubed over 3 minus x squared over 2 minus 6x. For the first one, we're going to evaluate from -4 to -2. We're going to do the exact same for the next 3 intervals, but they're going to be evaluated from those endpoints. So there's each one of our antiderivatives. So we took the antiderivative, evaluated from -4 to -2, the same antiderivative from -2 to +3, the same antiderivative from 3 to 4, and we're going to need to find the absolute value of each one of these antiderivatives evaluated at the endpoints. But only the middle one's going to be negative, so that's going to be the one that we need to find the absolute value of. Now, let's go ahead and plug in our endpoints. I'm going to do a little trick here. I'm going to be plugging in the endpoints to the same antiderivative, so I'm going to go ahead and just calculate my antiderivative evaluated at -4, and evaluated at -2, and evaluated at +3, and evaluated at +4. And then I'm going to be using these repeatedly. So I'm going to get -4 cubed over 3 minus -4 squared over 2 minus 6 times -4. I'm going to do the same thing for every one of the other points. And then if we get common denominators, we get -128 over 6 minus 48 over 6 plus 144 over 6. And when we do that, we get -32 over 6. I'm going to go ahead and calculate that for the rest of these examples. Whew, that is some serious calculation work right there. Importantly, we have our table of values right here. That's all we care about for this problem. So it's going to go back here to our actual answer. So what we're going to get is we're going to get f of negative 2, which is 44 over 6, minus f of negative 4, which is negative 32 over 6. That is our first term. And then we're going to add the absolute value of our antiderivative at 3, which is negative 27 over 6, minus our antiderivative at negative 2, which is 44 over 6. And you see we have negative 27 minus 44. That's going to be a negative number. So when we take the absolute value, we get our positive number that we're looking for. And then we're going to find f of 4, which is negative 32 over 6. And we're going to subtract f of 3. Oh shoot, we made a little error there. That should have been negative 81 over 6. I made an error in my original simplification. So we're subtracting by 81 over 6 here. As I was solving this out, I noticed that we made an error there because we had our 108 wrong there. And this is actually negative 81 over 6. Okay, so now we have all of our antiderivatives plugged in. Now let's do one layer of simplification. Whew, this is quite a doozy. So we have 76 sixths plus 125 sixths plus 17 sixths. And that gives us 218 sixths. And that is all we are going to do with this problem. You get 218 sixths. The main idea here, though, is that you need to find the zeros of the integrand and then split up your integral based on those zeros and take the antiderivative and then find the absolute value on each chunk there. All right, that was a lot of algebra. Let's go ahead and go on to the final example here. So this final example, we are trying to use a graph and interpreting the graph in the context of this problem. So this graph is meant to be the velocity at which Ryan is skateboarding. And we're trying to figure out how far he is from where he began and how far he traveled. Part A is the displacement, and part B is the total distance. Now we're going to calculate these by finding some areas. Note that our grid is going up by 1s and it's going over by 2s. So each box has an area of 2. So if we go ahead and find the area up here, we have 2. This whole triangle there makes up another 2. And then we have a half, so we get a 1. So this chunk right here is an area of 5. This chunk down beneath is a 2. And then these two combine together to be another, those are each 1. And then this is another half right here, so that's 1. So this area underneath is also 5. And then the area over here is 2 and 1. And this area altogether there is 1. So this area inside of this is 4. Therefore, our total displacement is 4 feet because it's plus 5 minus 5 plus 4, and that is equal to 4. Whereas the total distance traveled is 14 feet because that is a 5 plus an absolute value of negative 5 plus a 4, and so that gives us our 14 right there. And that's all the examples.